We're going to talk a little bit about basic photometry. We'll talk about this portable photometer, what we have to offer, the overview of the ranges that we offer that for, what each, the DT1, the DT2, the DT3, and the DT4 we're going to focus on, talk about the ranges and what parameters each one of those are good for. So depending on what you have a lot of controllers for, might help you pick one of those or another. So hopefully we'll talk about that. So photometry, it's the science of measurement of light. And we use that in the photometers. That's the DT series, and many other people have those to offer. You know, our competitors use those as a main source of developing what the residual is in a process, whether it be online where they take a sample periodically, or handheld units as well. And we have to be cautious because there are things that can corrupt that measurement. Okay, so we know that any dirt, debris, suspended solids in that sample that we're taking can corrupt it, because that science is we're shining a light through it, through that sample. After we add a reagent, that reagent reacts to whatever we're trying to measure, and it turns a different color of pink or red or purple, depending on how you look at that. And the more residual or the more leftover of that chemical, the more chemical that's in that sample, the darker or the denser that's going to show up as. And the darker or denser it is, as we shine that light through, it's not going to receive as much light on that photo detector on the opposite side. And conversely, if there's less residual in, it's going to react, that reagent's going to react to less, so you're not going to have quite the darkness in that sample, and more light's going to come through, and that photometer is calibrated to detect that light, and that light represents how much chemical is in that sample that we have inside. So quite often we use that DPD test. That's very common. The very long chemical name of that is at the end of that paragraph there of the third bullet point. And you don't really need to know that necessarily. Just it's DPD test. That's all we really need to know about it. And that's something we need to know. We do know that not only are we adding reagents to react to that, but in some cases we're adding buffers as well. And the one we have to pay particular attention to that is for what we refer to as the free chlorine, the HOCl that's in the process. And this is the dissociation curve. Whenever I talk to a person, I try to get them to find this dissociation somewhere outside of one of our publications, because it's not something that we have come up with. It is basic chemistry of the chlorine. So the thing is, they want most often HOCl in their process, because that's the good, decent, it's very effective for disinfection. Where the OCl minus, it also gives us some disinfection, but it doesn't have the efficiency that the HOCl has. In fact, depending on what publication you look at, the HOCl is 80 to 100 times as strong as the OCl minus. So where that comes into play again, for us trying to measure HOCl with our CLE sensor, for example, we are actually reading the HOCl in the process. A calorimetric test kit, just like the DT series that we have to offer, or other manufacturers, they offer calorimetric test kits. Not only are we adding reagents, but we're adding buffers. And those buffers change the pH of that sample. So you can see on that bell curve where at a pH of 8.5, we would only be reading slightly more than 10% HOCl. The rest of that chlorine has changed species to OCl minus. And remember, it is not the disinfection strength as the HOCl. So over the years, and we've seen this a lot, particularly because we're in that pump business. When people start adding sodium hypochlorite, in the past, they added chlorine gas. Chlorine gas kind of assisted with the problem that they were seeing here. And we'll talk more about this. The chlorine gas was acidic in nature, so it helped lower the pH of the process, actually. So where we were at pH 8.5, it may lower it to 7.5. You can see that the HOCl changes or is about 55% at 7.5. And the OCl minus would be 45% there. So it's much more effective. It's much more efficient for the disinfection strength. Where as you increase that pH, that disinfection strength drops off. You can see that on the bell curve. Well, now people calculate how much sodium hypochlorite they might need to use. They do tests at their end of their process and say, well, not only don't we have any residual left over, but we have growth, or our disinfection isn't what we anticipated it being. Well, that's because when they add the sodium hypochlorite is caustic in nature, it's going to increase the pH even further. So it changes from HOCl to OCl minus that much faster. So the disinfection can go down. So they say, well, maybe we miscalculated. This is a new chemical to us. We're not that familiar with it. Maybe our calculation was off. Let's add more sodium hypochlorite. Remember, it is caustic in nature. It drives the pH up further. Their disinfection could go down from adding more chemical. So we have to be aware of that. We have to instruct them and help them understand that. Some people are adamant about not changing the pH of their process. In fact, they want the pH to be higher. They say that they're concerned with corrosion in their system. So with that said, we just have to make them aware that that calorimetric test kit that they're using not only reacts because of the reagent in there, but it also buffers the sample. So where we might be at 8.5, the target is actually about 6.7, 6.5, depending on the manufacturer. So it tries to lower the pH there, and you can see how active or how much HOCl is there at 7 or 6.5 on the pH side. So it's much more efficient. It looks to be much more efficient, I should say. With our sensor, we're going to do that mathematically. We actually have to install a pH sensor, measure what the pH actually is, what we're reading as far as HOCl, and then we adjust it mathematically to try to match what the test kit is going to read. And we have to do that because the test kit has been around, this test method has been around forever. People don't really care about those parameters sometimes. They just want it to match. So to do that, we do it mathematically inside of the controller or analyzer. So you can see one of the photometers we have here. You're going to receive everything you need for out in the field. Comes in a nice, easy to manage box. You get the measuring chamber itself. You get the cuvets. You get several of those. You get a battery. Of course, it is an electrical device. You need a battery to power it up. You get the reagents. You get a little mixing covet cleaning brush also. A little thing to smash some of the tablets that are in the box there on the far right. The phenol red and whatnot. So everything you need is basically included when you get that. It's a very good tool to have out in the field. If you're selling a package where you're selling the pumps, you're selling the controller. Hey, can I get you something to help with your calibration needs out in the field as well? So the DT1, which is a very common unit, you can see at the very top, it could do calibrations for free and total chlorine up to 6 milligrams per liter, or 6 parts per million. And that is a pretty good range. You know, you don't see above that too often. But if you know that it's more than that, or you suspect that it's more than that, what could happen, remember we're dealing with chlorine, it's a bleaching product, it could bleach that color back out of your sample. So if you suspect that you're above 6 ppm, or you know, it just is odd that you're not above that, what you can do to read that above that is maybe do a dilution. So you would take 10% sample from your process, and maybe, I'm sorry, 50% sample from your process, and 50% of that sample comes from, say, polar water or spring water. You put that into your DT test kit, and then your result, you just double it. Or you might have to do a 10-to-1 dilution. So now you do take 10% of your sample from your process, and the other percentage is from the spring or polar type water, and you multiply your results by 10. So there's ways that you can kind of read above what the limitation is for that chlorine as well. Of course, it can do bromine. This is all in the DT1 test kit. Chlorine dioxide, which is of interest for several people out there. Now, we'll talk about that on the DT4 as well. It's nice to be able to do that right in the field instead of having to take it to a lab to do that sample. Ozone, phenol red tablets are included there. That's, I mentioned, they're in that box. That's to establish a pH. And that might come in handy if you don't have pH buffers from time to time. You can at least get a known value of what that sample represents. And then that chloranic acid, that's used in pools sometimes, maybe some other processes, to kind of help the chlorine be maybe like a slow release chlorine, we'll call it. So, you know, some people may want to test for that. You can see the ranges that are available there. It's very wide ranging. The DT2 test kit is a little bit limited on the parameters that you can sample with that, but those parameters may all fit very close hand in hand. For example, you have fluoride, you have your free chlorine and total chlorine, and chlorine dioxide. So those first several could very well be in municipal applications, or you might have one application that's using chlorine dioxide. So that could fit best for your process. Now the DT3 test kit, moving on to that, you can see is a little bit different on what it includes. You see, of course, it shows the photometer itself, the reagents, for hydrogen peroxide now. And hydrogen peroxide seems to come and go in popularity. It kind of rides away for a little while, and I'm sure that has to do with the cost of the hydrogen peroxide that's out there. But it's a very good oxidant, just depending on how much people are willing to spend to do that disinfection, they might do that. Sometimes in industrial applications, we find that a little bit more often. You get some of those little cuvets again, those little round cells or cups. You can do your tests right in those, and this one has a cover on it as well. So you can see that everything again is neatly packed in a nice carry case for you. As I mentioned, you can do hydrogen peroxide, and you can do that right in the field. The alternative might be where you have to take that sample and take it to a lab and do a test with a titrator, or another type of calorimetric test. They have field titration tests as well. and it depends on how many drops of the titration chemical that you put in, and each one is maybe represents 7 parts per million. So you're somewhere in between that depending on how many drops you put in, that range of 7 parts per million. Well, if you want it more accurate, this unit might be what the customer's looking for. You can see the ranges up to 50 parts per million or up to 500 parts per million. And you want to set that accordingly to what you think you're closest to, again, so you're a little bit more accurate. The DT4, which we mentioned a little bit previously, you can see it's pretty busy on what all it includes. Of course, you have your buffers and reagents up in the top, number 4 there, and you can do DPD tests with that. The stir, number 2, we need to strip out any of the chlorine dioxide in order to do a chlorite, sodium chlorite test. And those go hand in hand. This can also measure chlorine dioxide. So chlorine dioxide and chlorite, those are 2 kind of hand-in-hand chemicals there. In fact, sodium chlorite is a byproduct of the reaction when chlorine dioxide is consumed. So what's left over is the sodium chlorite. And sodium chlorite is limited on how much can be in a system. So we need to know that. Of course, we have a chlorite sensor that measures it in real time. But again, to calibrate that sensor, this test kit could help you with that. And it's pretty exclusive. I don't know how many manufacturers have the chlorine dioxide and chlorite in one test kit. So that could be helpful for you. The ranges on chlorite up to 2.5 ppm, which is quite high. I think typically people look to limit it to 0.8 ppm, no more than that. So should well be able to handle the chlorite. And also the accuracy on this unit is pretty good. We use a liquid for the reagents, and that's nice because excuse me, we pour that sample in over there, and it can help us form some of the scale that can corrupt some of the other type of powder pack units that are added after you already have the sample in. So there are some advantages. Again, with our unit, with other manufacturers' units, any kind of suspended solids in that water can cause shadows, it can cause reflections. If you get fingerprints on the little sample jar, that can cause a problem. If you don't clean the sample jar regularly, you leave it stained. That, of course, is going to show up. It's not going to let as much light go past, and it's going to look like you have more residual in your application than you potentially actually do. So it's very important to know about what can cause problems with that, educate the customer, let them know the benefits to that. On this DT4, this could be very good for one of the DACs that has chlorine dioxide sensor and a chlorite sensor. You can calibrate both of those with the DT4. So it's a very beneficial way to package that all together going out to customers.